everybody. I'm going to go over a little bit in terms of acid base and how we determine most acidic, least acidic, and kind of what factors we're going to use. So the book presents it as Ario. So Ario is the acronym that we're going to be using to kind of keep us looking at these things in the right priority. So before we get going on those though, I do just want to make sure that we keep in mind that the more stable conjugate base is going to come from the more acidic proton, and the more stable conjugate acid is going to come from the more basic atom. Okay, so what you should be thinking about here is you should be looking at charged structures. Okay, and those charged structures are going to be much easier to compare stability than if you're looking at two neutral molecules. That becomes really difficult. So the factors that we're going to use, A is going to be atom. Okay, what atom is your charge on? That makes a huge difference in terms of how well that charge is going to be stabilized. 2 is resonance. Okay, is that charge delocalized? That delocalization is going to help stabilize that charge. I is induction. Okay, induction has a lot to do with what we talked about earlier at the beginning of the class when we were trying to find polar covalent bonds and inductive features and everything. And that's just electronegative atoms that are nearby that are going to help pull away some of that electron density. Not really resonance delocalization, it's a more mild effect, but it still helps to stabilize that charge. And then O is going to be orbital. Okay, and that just means that the orbital itself that the lone pair is held in does have a pretty big impact on how stable that charge is, depending on what orbital it's in and where its location is compared to the nucleus of the atom. Okay, so first one is atom. So what we're looking for atom is the more electronegative atoms we have the negative on, the better we are. Also, larger atoms are going to stabilize that negative charge better. And that's just keeping in mind that if you've got something really small and you've got a whole bunch of electron density on it, that's hard to keep all of it contained. But the bigger you are, the more you can spread that out. And it's just easier to have that more stable. So if I'm looking at these two, why is this so hit or miss? If I'm looking at the top two options, if I look here, they're all neutral. Okay, so if they're neutral, I need to do something to get them to a charged state. So in that case, what I'm going to do is I'm just going to pretend that I have a fake base here. So you'll often see me use just kind of some generic base. We're going to go take that proton, break that OH bond, and give a lone pair to the oxygen. So what I've done here is I have drawn a conjugate base. Okay, so this is my conjugate base. And I'm going to do the same thing over on this side. Use my base, take that H, give a lone pair. And now I've got two charged structures. Okay, so now it's going to be much easier to compare these two and ask ourselves, okay, which of these is the more stable conjugate base? And whichever one is more stable, that's the more acidic proton, okay? Because what we're looking for is we want a conjugate base that can be nice and stable, and that means that the proton is easy to get taken off if that conjugate base is nice and stable, right? That's a nice kind of dip down in terms of energy. So it's not that hard to get to it. Okay, so in this case, I gave a pretty easy example. We've got oxygen versus nitrogen. Oxygen is more electronegative. Nitrogen is less electronegative. So the oxygen is going to be more stable, whereas this one's going to be less stable. So this is going to be our more acidic one, the alcohol, whereas the amine is less acidic. Okay. So the other way that you can think about this is if you're looking at your conjugate bases, this is a stronger base. Okay, so it wants to get a proton and go back to the neutral form here. This one is a little bit more okay, just chilling. Okay, so more acidic, more stable conjugate base. If I've got a stronger conjugate base, it's going to be less acidic. Okay, but it's going to make a pretty good base. All right, so then if we look at the bottom example here, I'm going to scooch this down a touch. Okay, so again, we're going to do the same process of first drawing out our conjugate base. And this should be something that you get into the habit of doing, is just always drawing out those conjugate bases. Because most of the time we're going to be faced with a neutral acid. And so we're going to need to draw out that conjugate base to find our charge. Okay, so now I've got oxygen versus sulfur. So keep in mind here, if I just kind of throw up my basic, that's basically all the periodic table that you really need. I guess you can kind of throw aluminum on there too if you really want to. So what we're looking at here is up at the top where we had oxygen versus nitrogen, we had electronegativity going to the right. So when they're in the same row, we want to focus on electronegativity. In the same column, we want to focus on size. Okay, so sulfur is much larger than oxygen because now we have another kind of shell of electron density around it. So sulfur is larger than the oxygen. So that makes this conjugate base more stable, which in turn makes this more acidic. And this is going to be the least acidic. Okay, so that one is all about size. O is smaller than S. Okay, so let's move on to resonance. So for resonance, we're looking at delocalized charge. Okay, so remember, any delocalized charge is going to be a lot more stable than localized charge. But there is a caveat to this. You do need to keep a close eye on what atoms the charge is landing on. Okay, because as we've just talked about, the atom that the charge is actually on is incredibly important. That's actually our first top priority. So if I have a whole bunch of resonance structures, but they're not necessarily good, they're just putting a negative on like a carbon a whole bunch of times, that's not necessarily going to be a more acidic proton because you're not putting that charge on really electronegative atoms. Okay, so let's take a look at what that all kind of looks like. So let's just start with a simple example first. So again, we're going to start with drawing out our conjugate base. So I have this and then my conjugate base over here. Okay, so if I'm looking at these two conjugate bases now, I've got two H's here. That is localized. Okay, that charge cannot move anywhere. That is stuck on the oxygen. But if I look at the structure on my right, that's the conjugate base of acetic acid. I do have that pi bond nearby, so I can do my lone pair next to pi bond pattern. Push the electrons up, making sure that you do the right arrow here. So we're not doing equilibrium arrows, we're doing a resonance arrow. So now I have that. So this one, I've got my charge delocalized. Not between, over two oxygens. Okay, that's a really powerful combination, having it delocalized over two very electronegative atoms. So in this case, this is the more stable, which makes this the most acidic, and this is the least acidic. Okay, all because that charge delocalization is going to be much more stable than a localized charge, especially when we're considering the fact that they both have charges on the same atom, right? So if we look at the Ario acronym, we're looking at A is the same, right? A is oxygen in both of these cases. So then we're looking at the next one, which is resonance, okay? If we look at the next example here, again, we're going to do the same process of drawing out our conjugate base. Drawing out conjugate base. Okay, so if I look at these two options, on the left-hand side, I can do resonance here. Okay, and it's a pretty good resonance structure because I've got a negative charge on the oxygen. This one is localized, but because carbon is not as electronegative as oxygen and has a harder time stabilizing that negative charge, this is actually the most acidic. With the localized charge on the oxygen because of the atom reason, because it's electronegative. So the delocalized charge over here, it's not happy to share it between oxygen and carbon. So that charge doesn't really want to be on the carbon and the oxygen. It's actually better off just being on the oxygen. Now, if I change that carbon to an O and I had an OH, then that would certainly be more acidic. But at the end of the day, this is more acidic than this is. And to be fair, they are fairly close. And we'll be talking about kind of a quantitative way of being able to determine acidity, so that when you've got a situation like this where it's kind of close, then we will have a more defined way of kind of delineating these two acidities. So this is something I wouldn't necessarily expect you to pick up on just using Ario, but I just want you to be sure that you're thinking about all these things together and making sure that you're not just going, oh, well, there's a ton of resonance, therefore it is more the more acidic one. All right, I'm gonna scooch our induction one down here a little bit. Oops, that's not it. Okay, so for induction, we are looking for electronegative atoms. So if you don't have really electronegative atoms around, don't even think about induction. It's a bit more of a minor effect, as you can see, it's ranked below resonance, because resonance is a physical delocalization. Like, it's pretty aggressive in how it does it. It just kind of spreads it all pretty evenly. Induction is a lot more mild of an effect because you can't draw any arrows, right? You can't draw any electron arrows to kind of push things around. It's really based on just kind of pulling small bits of electron density towards the electronegative atoms. So we're really looking at that kind of effect. And it's a lot to do with kind of finding those polar covalent, dipole type directions. So if I have the compound on the left here with all the fluorines, you can tell that I have something like this going on with that, where I've got a lot of electron density being pulled away from that kind of right-hand side of the molecule. So if I go to my conjugate base here, so essentially what I have going on is I've got all those fluorines pulling electron density away from that negative charge on the oxygen and kind of getting pushed into, kind of pulled towards the fluorines. So if I have this, okay, they have the same amount of resonance, they have the same atoms, but the only difference is that one of them has those fluorines nearby. That's going to help withdraw a little bit of that electron density. Okay, and that happens inductively. It's more through the sigma bonds, not really through pi electrons. Okay, but same amount of resonance. This one is going to be more acidic, and this one is going to be least acidic. Okay, so it is important to note that this effect does decrease with distance between electronegative atoms. Okay, so if I drew up another one and put the fluorines just one carbon away, that would be less acidic than the one where the fluorines are right next to it. All right, and then our final option is orbitals. So this is kind of your last thing to look at. It's the lowest priority. It's the one that comes up the least often. And I will say it mainly comes up because you're looking at something like this. So if you're looking at an alkyne, that might be your kind of indication that, hey, maybe I should think about orbitals a little bit. But most of the time you're going to see this effect on carbon atoms, and carbons tend not to be the most acidic things in the world because, as we've already seen, they don't really like to have negative charges on them because they're not that electronegative. It's okay if they're in resonance. It's, okay. Induction is going to help just as much as induction always does. And then orbitals are going to be kind of our big ticket item in terms of how we're looking at acidity on carbon. So the thing that you want to keep in mind here is that it's more stable to hold electron density closer to the positively charged nucleus. So the nucleus of the atom is going to be the most positive place. Having positive and negative together is good, right? So if we have more of that kind of centered around the nucleus and not floating out in la la land somewhere, that's going to be a more stable conjugate base. So the way to get stuff closer to the nucleus is we want a higher percentage of s orbital in that kind of hybridized system. So the s, remember, if we have a nucleus, the s orbital is just a circle right around it. Okay, so s orbital. It has the electron density right around the nucleus. So that's about as close as you can be to a nucleus. A p orbital, though, is more this shape. And there's actually no electron density right at the nucleus. Okay, there's actually a node at that point. So there's no electron density here. So the way to get electron density closer to the nucleus is to have more s. So I pulled this figure out of the book. So remember, when we're averaging all these atomic orbitals together, we've got 1s and 3p orbitals to make up the sp3 system. So you can see that there's more of that kind of p shape to the sp3 orbital. And then once I start taking out some of that p, then I'm essentially increasing the quantity or the ratio of s to p in the system. And so you can see my orbitals keep getting a little bit shorter. They get a little squatter, a little rounder, because now I've got, up to 50% s in my sp orbital. So the more electron density I can have around that nucleus, the better it's going to be. So if I'm looking at this, again, I'm looking for the conjugate base. So I'm going to end up with something like that for my alkyne. And then something like this for my alkene. So this lone pair is in an sp orbital. This lone pair is in an sp2 orbital. Oh boy, that really got away from me. Okay, so this is going to have more S character, and that's what you'll usually hear said in books is like S character. This is less S character. So this is more stable, less stable. So that makes this more acidic and then less acidic. Okay, so generally you're going to go through this process thinking about atom, resonance, induction, orbitals, and kind of go through that until you find a difference, and then deciding which of those is going to be the more stable conjugate base or conjugate acid, depending on what you're looking at. So as always, let me know if you have any questions and have a great day.